Section: Introduction. In this section, we introduce our work on contrastive pre-training, initially known as convert for medical imaging, which later evolved into CLIP. This approach utilizes large sets of image-text pairs with a specific loss function called InfoNCE, allowing models to classify and retrieve images without needing manual labels. Notably, this pre-training can be applied to various modalities, including audio and video, leading to the development of the six-modality model, ImageBind. Despite its versatility, CLIP's foundational design has remained largely unchanged, specifically the use of L2 normalization for embeddings and cosine similarity for softmax logits. Desai introduced Meru, which instead lifts embeddings onto a hyperbolic surface, allowing for a different distance metric and enforcing hierarchical relationships between text and images. Interestingly, they identified CLIP's embedding space as Euclidean, even though L2 normalization positions the embeddings on a sphere, a characteristic of elliptic geometry. Additionally, cosine similarity in CLIP does not function as a negative distance metric, raising questions about the effectiveness of the softmax logit choice. To explore these questions, we systematically tested various embedding geometries in contrastive language image pre-training models, focusing on the less explored Euclidean geometry. Our findings indicate that using cosine similarity or negative geodesic distance in elliptic geometry yields similar results. In both Euclidean and hyperbolic geometries, we observed that the final normalization layer in transformers negatively impacts performance, while using the squared negative distance logit outperforms the standard negative distance logit, likely due to implicit regularization. We also found that our Euclidean CLIP, EuCLIP, performs as well as or better than CLIP and supports hierarchical relationships comparably to the more complex Meru. In the related work section, we discuss alternative pre-training objectives for language image models, such as COCA, Otter, and SIG-LIP. COCA incorporates a captioning loss alongside InfoNCE, while Otter considers similarities between text and images more broadly. SIG-LIP, on the other hand, employs logistic regression on text-image pairs instead of contrastive loss. However, aside from Meru, the exploration of alternative softmax logits remains limited. We also review the comparison between hyperbolic and Euclidean geometries, noting that earlier work by Nicol-Keela suggested hyperbolic embeddings were better for predicting hierarchical relationships. This was contested by Bansal-Benton, who argued that Euclidean embeddings can perform competitively when their norm constraints are relaxed. Ganea proposed an alternative loss function for similar tasks, and in reinforcement learning, Chaitin compared hyperbolic and Euclidean embeddings for state representation. In computer vision, Krolkov introduced hyperbolic protonet for classification and compared its performance to Euclidean protonet. Lastly, we address the role of layer normalization in transformer architectures, which has been a topic of much discussion. Initially, layer normalization was applied after residual blocks, but later versions placed it within the blocks. Most pre-lane transformer architectures, including vision transformers, have since added a final layer normalization, a change that has not been thoroughly examined. For our language image pre-training, we utilize a dataset of text-image pairs, dividing them into mini-batches to facilitate learning representations. Section Summary. In this section, we explore the evolution of contrastive pre-training models, particularly focusing on the transition from CLIP to Meru, which utilizes hyperbolic geometry for improved hierarchical relationships between text and images. We also investigate various embedding geometries and softmax logits, finding that our proposed Euclidean CLIP, EuCLIP, performs comparably or better than CLIP while supporting hierarchical relationships effectively. Section: Contrastive loss. In this section, we explore contrastive loss as a pre-training objective where our model learns to associate images with their corresponding text and vice versa. We assume we have a text encoder and an image encoder, allowing us to treat images and text as context. We apply InfoNCE twice to derive the contrastive loss, which involves a similarity function and a logit scale, with the density ratio expressed in terms of the similarity between the text and image embeddings. When we use cosine similarity as our similarity function, we find that it leads us to the loss function used in CLIP. However, the connection to geometry is not straightforward since cosine similarity is a decreasing function related to the geodesic distance on a specific sphere. We refer to the geometry underlying CLIP models as CLIP geometry. Alternatively, we can use negative geodesic distance on the sphere as our similarity function, which maps pairs of embeddings to a different range but maintains the order of cosine similarity. We also consider Euclidean geometry, which is intuitive but less explored for contrastive pre-training. Here, we define distance simply as the difference between two embeddings. To make the logit scale more comparable across different geometries, we scale the embeddings and use a modified similarity function based on the Euclidean distance. We also look at using the negative squared Euclidean distance as a similarity function for two reasons. It simplifies the calculation and may improve the distribution of the L2 norm for positive pairs. Additionally, we can interpret the squared distance logit as a linear model when considering one modality's embeddings as prototypes. For hyperbolic geometry, we follow the Meru model, which uses a similarity function defined by three trainable parameters. We scale the encoder outputs and use a curvature parameter to map embeddings to a hyperboloid structure. The similarity function here is based on the negative Lorentzian distance between embeddings, and we also consider using the negative squared Lorentzian distance. Lastly, we discuss entailment loss, which measures how much a more specific concept deviates from a generic concept's embedding. This concept was initially proposed for modeling hierarchical relationships in WordNet and has a transitive property. Recognizing that images are often more specific than text, we incorporate entailment loss into Meru to reinforce this relationship. Section Summary. In this section, we explore various contrastive loss functions for pre-training models, including cosine similarity, negative geodesic distance, Euclidean distance, and hyperbolic geometry, each with unique scaling and similarity formulations. We also introduce entailment loss to model hierarchical relationships, emphasizing the specificity of images compared to text. Section Euclidean. In this section, we introduce a modified version of the Euclidean entailment loss. We define the entailment cone for an embedding in Euclidean space based on a half aperture, where the minimum radius, denoted as k, is a hyperparameter. However, this approach leaves the entailment cone undefined for embeddings with a norm less than k. To address this, we adjust the value of k divided by the norm of the embedding to ensure it is defined across all dimensions. We note that transitivity may not hold for embeddings with a norm less than k. For the hyperbolic entailment loss, we again follow the Meru formulation. In the hyperboloid model, the half aperture is similarly defined, and we ensure it is applicable for all embeddings by clamping the value of 2 times k divided by the square root of a constant c and the norm of the embedding to 1. The exterior angle formed by the origin, the embedding, and another point is also defined. The entailment loss remains consistent with the Euclidean case in terms of the aperture and exterior angle. For both Euclidean and hyperbolic models, the total loss combines the continuity loss and a weighted entailment loss, where the weight is another hyperparameter. We conducted all experiments using PyTorch version 2.0 or higher, along with a modified version of EuCLIP. We specifically utilized the VIT-B32 and VIT-B16 implementations, keeping the text and image encoders unchanged except for the final layer normalization. In our data preparation, we initially tested the code and refined the hyperparameter range using the first million text-image pairs from REDCap's version 1.0. However, our main experiments utilized small and medium-scale datasets from Datacomp. We applied a filtering method that yielded the best zero-shot performance, using the top 30% of examples based on the CLIP score for the small scale and a combination of CLIP score filtering and image clustering for the medium scale. Between October and November 2023, we successfully downloaded a significant percentage of images from both filtered datasets, which explains the performance discrepancies between the Datacomp paper and our results. We also adopted the zero-shot evaluation protocol from Datacomp, modifying its evaluation code to accommodate different embedding geometries. In our results and discussion, we highlight that due to the qualitative differences between the small and medium scales, we cannot use the small scale for hyperparameter tuning. Our head-to-head comparison of the VIT-B16 model shows that EuCLIP outperforms both CLIP and Meru across all zero-shot metrics used in the datacomp evaluation. While DeSize models were trained on a larger dataset, our models still demonstrated consistent performance on ImageNet. We observed expected structures in the embedding space, where text embeddings are drawn towards the origin and image embeddings are pushed away, unlike the overlapping embeddings seen in CLIP. We also performed image traversals, interpolating between image embeddings and the origin, but found no significant differences in the distinct captions retrieved by the three models. The results for Meru remained unchanged regardless of the filtering applied, while a clearer representation hierarchy emerged with EuCLIP when adjusting the value of K. For further details on image traversals and results, we refer to the supplementary material. Section Summary. In this section, we present a modified formulation of Euclidean and hyperbolic entailment loss, ensuring that the entailment cone is defined for all embeddings by clamping parameters, while also detailing our experimental setup using PyTorch and datacomp datasets. Our results indicate that our VIT-B16 models outperform existing models in zero-shot metrics, demonstrating distinct embedding structures influenced by the entailment loss. Section. VIT-B32 Model Experiments. In this section, we present our experiments with the VIT-B32 model at a medium scale. The table shows all the relevant models we trained. We find that, except for the impact of entailment loss on retrieval tasks, using Euclidean geometry, squared distance logit, no final layer normalization, and training with entailment loss generally performs better than hyperbolic geometry, regular distance logit, unmodified encoders, and training without entailment loss. The Meru combination is less favorable, and when we use no final layer normalization, it becomes unstable. In contrast, EuCLIP without entailment loss matches CLIP's performance. We note that in a 512-dimensional embedding space, the volume of the epsilon ball increases significantly, indicating that the benefits of hyperbolic geometry are minimal in practice. Previous studies have shown that hyperbolic space is advantageous for small dimensions but loses its edge as dimensions increase, which we expect to be common since we often work with hundreds of dimensions. Throughout our training, we observe that the curvature parameter consistently decreases, with all our hyperbolic models and Meru checkpoints settling at a minimum curvature of 0.1, confirming the disadvantages of hyperbolicity. While we have limited insights into the role of entailment loss, we can address whether text and image embeddings separate naturally. By comparing the distance distributions of EuCLIP and Meru with those trained without entailment loss, we find that the distributions overlap and appear identical for EuCLIP with no entailment loss. Interestingly, these performance trends do not apply at a smaller scale, where CLIP and elliptic geometries perform better. We hypothesize that with limited training data, the restricted embedding space forces the model to learn underlying structures rather than memorize, and the training budget limits the effectiveness of both Euclidean and hyperbolic geometries. We will discuss the final layer normalization in the next section. In our final layer normalization ablation experiments, we controlled for changes by only altering one factor at a time. This approach raises questions about the impact of removing final layer normalization and whether its effects are additive. We conducted additional experiments by restoring the final layer normalization in the EuCLIP models. Our results show that restoring the final layer normalization significantly improves model performance. In fact, the VIT-B16 model with final layer normalization only slightly outperforms the VIT-B32 model without it, despite having 4 times as many patches. Examining the architecture of the text and image encoders, we see they utilize a version of layer normalization with learnable parameters, followed by a linear layer. The final embedding can be expressed in terms of these parameters and a normalized vector. The linearity allows us to represent the final embedding in a simplified form, indicating that it resides on a hyperellipsoid defined by the parameters. The loss of degrees of freedom due to the absence of final layer normalization cannot be regained. We draw a parallel to previous work, where it was noted that Euclidean embeddings become competitive when L2 norm clipping is relaxed. Our findings suggest broader implications, as the pre-lane transformer architecture without final layer normalization is unique in that its output does not undergo layer normalization. Other transformer architectures may face similar performance issues if their output norms are relevant, potentially leading to unfair rejections of novel architectures or loss terms due to this incompatibility.